Okay, welcome everyone to the last lecture of Unit 1. This is the last of the lectures that will have content for our first exam. All lectures that come after this will not be on the first exam. But remember, in this class, all exams are somewhat cumulative, so the material that we've covered up through the end of this lecture could be on any exam this semester. So don't flush this material, not only for that, but like I've said in the very beginning, everything builds on everything that's come before. So all the stuff that we've talked about so far, I promise will come back in the coming chapters. So let's begin with our not really attendance questions. In what way would EPO affect PR? What mechanical event occurs during the QRS complex? And what is the function of prothrombinase? So let's see what these are. In what way would EPO affect PR? Well, EPO is erythropoietin. That's the hormone that triggers erythropoiesis, formation of red blood cells, erythrocytes. So EPO would increase hematocrit. And when we increase hematocrit, that increases blood viscosity. It makes the blood thicker. And if blood viscosity is increased, that increases peripheral resistance. What mechanical event occurs during the QRS complex? Well, there's several things that occur during the QRS complex. Two of them are electrical events. We have atrial repolarization, and we also have ventricular depolarization. But this is asking about a mechanical event. The mechanical events are things like systole and diastole. So during the QRS complex, we also have atrial diastole. The atria relax. That's a mechanical event. What is the function of prothrombinase? Prothrombinase is an enzyme, and its function is to convert prothrombin into thrombin. That's during the formation of the fibrin clot. Maintaining blood pressure. So everything from this point through the end of this lecture will be focused on either maintaining or regulating blood pressure. And then at the end, we may talk about a couple of disorders. So make sure you have your blood pressure chart handy. We will refer to that quite a bit. Now, when we're talking about blood pressure, remember blood pressure is found by cardiac output times peripheral resistance. Those are the two ways that we can influence blood pressure. We've already said that cardiac output can be influenced by stroke volume or heart rate because those are the two things that we multiply together to get cardiac output. Now, we can regulate stroke volume, we can regulate heart rate, and we've looked at the ways that we can regulate each of those. But let's now go a little bit deeper. When we talked about stroke volume, we said the ways to regulate stroke volume were either regulating preload, EDV, regulating contractility, the force that the heart contracts with without regard to stretch, and afterload, the pressure in the aorta prior to ventricular systole and ejection of blood. Now let's go back and look at the factors that affect EDV. So real quick, let me pull up our chart here to show you what we're going to be talking about. So number 1, number 2, and number 3 were the 3 ways to affect stroke volume. Now we're specifically looking at number 1, preload. And there are 2 ways to affect preload: venous return and ventricular filling time. We're going to talk about those. We're also going to see, and this can get a little bit confusing if you're not sure how to read this, the ways to affect venous return are exercise and blood volume. And the ways to affect blood volume are all of these with the dash in front of it. So the things with the dash just affect blood volume. And either blood volume or exercise will affect venous return. So we're going to come back to this in a little bit and see how to use this to draw out some flow charts. But back to the lecture part here. So venous return, we just said exercise and blood volume are how we affect venous return. Exercise, we actually talked about a little bit when we were talking about how veins work. Remember, the pressure in veins was really, really low. And they had those valves that let blood flow through one way, but not the other. And since the pressure was so low, rather than depending on the pressure from heartbeats, instead it depended on our body moving around. It depended on those muscular pumps and also the respiratory pump. So changes in pressure when we breathe. Now, when we exercise, both of those things are going to increase. When we're exercising, we're moving our muscles more. So remember how the muscles worked to squeeze on the veins and kind of milk the blood through? Well, if you're exercising and you're moving those muscles more, then you are pushing the blood through those veins faster. In other words, you are increasing venous return. Also, when you exercise, you're breathing more. You're breathing deeper, you're breathing faster. So the respiratory pumps, those pressures in the thorax are going to be changing repeatedly. And again, that's going to increase venous return by squeezing on those veins. So an increase in exercise increases venous return, which increases EDV, which increases stroke volume, which increases cardiac output, which increases blood pressure. So let's go and pull up our chart again, and I'll show you how we can write that out. Heart rate, that's its own thing. Stroke volume right now is going to be what we focus on. Yes, when you exercise, your heart rate goes up, but that is for a completely different reason. We'll talk about that later on. Here, we want to talk about what exercise does directly. So when there is an increase in exercise, when we are exercising, that's going to cause an increase in venous return for all those reasons that we just talked about. And when there's an increase in venous return, there's going to be an increase in preload, or we could also have said EDV. I tend to say EDV. It's just easier for me to write. And when there's an increase in EDV, there's an increase in stroke volume. And when there's an increase in stroke volume, there's an increase in cardiac output. I've run out of room here, so I'm just going to continue. When there's an increase in cardiac output, there's an increase in blood pressure. All we did was work our way up. So let's see. When there's an increase in exercise, when we're exercising, we work our way up. There's an increase in venous return. When there's an increase in venous return, there's an increase in preload, or EDV. When there's an increase in EDV, there's an increase in stroke volume. When there's an increase in stroke volume, there's an increase in cardiac output. And cardiac output, or PR, are the two ways to affect blood pressure. When one goes up, blood pressure also goes up. So when there's an increase in cardiac output, there's an increase in blood pressure. And that's how this chart works. Now we'll come back and do some more here in just a moment. Blood volume. So blood volume is just what it sounds like, the volume of blood in your vessels. If there's more blood volume, if you have more blood in your body, then there will be an increase in venous return. More blood in the body, more blood comes back to the heart. Or if blood volume is down, let's say you're hemorrhaging, If blood volume is down, if there's less blood in your body, then less blood will come back to your heart. Venous return would be down. So looking at our chart, I won't pull that back up just yet. Looking at our chart, underneath there we saw hemorrhage, which is what we just said. And then we see several hormones and also salt, or on the chart it's sodium, but we can talk about salt. So the first hormone, ADH, we've mentioned it, and I said that it would come back all semester long. ADH, the anti-diuretic hormone. Well, most people have heard of a diuretic. If you haven't heard of a diuretic, I'll tell you what it is in just a moment. If you have heard of a diuretic, what does a diuretic do? Well, a diuretic makes you pee. And they make you pee because of blood pressure. When someone's given a diuretic, typically they're given a diuretic because they have high blood pressure. So what would an anti-diuretic do? It would make you not pee. It would keep water in your body longer. So ADH, the anti-diuretic hormone, we saw before that it was a vasoconstrictor. Here we're going to talk about something completely different. This is actually the bigger thing, the more well-known thing that ADH does. ADH, really what it does is it tells your kidneys to reabsorb water before it leaves your body as urine. ADH tells your kidneys to reabsorb water before it leaves your body as urine. So water remains in your body longer than it would have otherwise. So ADH increases blood volume, which increases venous return, which increases EDV, which increases stroke volume, which increases blood pressure. Next, aldosterone. Similar to ADH, but it functions differently. Aldosterone tells your kidneys to reabsorb sodium before it leaves your body in the urine. So sodium that's just about to leave your body in urine, aldosterone tells your kidneys, no, let's hold on to that. So that sodium is placed back into your blood. Why would we want to hold on to sodium? Think back to Bio 137, especially if you had me in person. What is sodium? Sodium is a solute. And what do solutes do? Solutes suck, okay? What that means is solutes pull water towards themselves. Solutes suck water towards themselves. So if aldosterone tells your kidneys to reabsorb sodium back into your blood, wherever that sodium goes, water is going to follow it. So aldosterone tells your kidneys to reabsorb sodium, which results in reabsorption of water. And if we reabsorb more water, then your blood volume is going to go up. And if your blood volume goes up, venous return goes up, which leads to increased EDV, which leads to increased SV, which leads to increased CO, which leads to increased blood pressure. We'll write these out here in just a moment. Salt intake. Well, eating salt is really the same thing as what aldosterone does at your kidneys. It's just rather than your kidneys reabsorbing the salt, here we are just putting salt directly into our blood through our diet. If you eat more salty foods, then sodium and chloride, the other part of salt, are going to remain in your blood. And if there's more salt in your blood, if there's more sodium and chloride in your blood, then you're going to have more water in your blood. More water is going to remain. So blood volume would go up, which would cause an increase in venous return, increased EDV, increased stroke volume, increased cardiac output, increased blood pressure. That is why eating salty foods raises your blood pressure. Atrial natriuretic peptide, ANP. We mentioned this when we were talking about vasodiameter and peripheral resistance. Now we're going to look at something that it does as regarding blood volume. Well, ANP blocks the effects of aldosterone. It does something else too that we will see when we get to kidneys. But ANP blocks the effects of aldosterone, which means we do not reabsorb as much water. So more water leaves in the urine. Our blood volume drops. So as ANP is increased, blood volume is decreased. Venous return is decreased. End diastolic volume is decreased. Stroke volume is decreased. Cardiac output is decreased. Blood pressure is decreased. So let's go back now that we've covered all of those and look at our chart. We've now covered all of these factors that affect blood volume. And if we affect blood volume, we affect venous return, and we work our way up. So let's do one of these flow charts that's pretty straightforward, and then we will do one that's a little more tricky. Let's look at what happens when there is an increase in sodium. When we have increased sodium, work our way up the chart here. If we go up, the next thing we come to is blood volume. Yeah, sodium is written underneath all of these things, but we go up to the next level. So we're here at the dash level, we go up to the next level, blood volume. Increased sodium causes increased blood volume. And if we have increased blood volume, go up to the next level, the one with the letter in front of it, venous return. Increased blood volume causes increased venous return. Next level, the number, EDV. Increased VR leads to increased EDV. Next level, stroke volume. Increased EDV leads to increased stroke volume. Next level, cardiac output. Increased cardiac output is one of two ways to affect blood pressure. So that's what our flow chart would look like. Increased sodium leads to increased blood volume, leads to increased venous return, leads to increased EDV, leads to increased stroke volume, leads to increased cardiac output, leads to increased blood pressure. All right, let's do one that's a little bit more involved. Let's look at what happens when there's an increase in ADH. All right, I'm going to write this across the top so I have more room. When there is an increase in ADH. Well, we see ADH right here. Increased ADH causes increased blood volume, which causes increased venous return. Increased blood volume, increased venous return. Keep working up. Increased end diastolic volume. Increased what? Stroke volume. What's next? Increased cardiac output, which leads to increased blood pressure. Seems straightforward, but that's not the end of it, because we also have ADH written over here, independent of the ADH that's written over here. So what we will see is sometimes one factor can influence blood pressure more than one way. So we're going to have a completely separate row, and these two rows are completely unrelated to each other. So increased ADH, we see also affects vasodiameter. So ADH causes a decrease in vasodiameter. It does that by causing vasoconstriction. Remember, the other name of ADH was vasopressin, or sometimes arginine vasopressin. And vasodiameter is one of three ways to affect peripheral resistance. When vasodiameter goes down, peripheral resistance goes up. And peripheral resistance is one of two ways to affect blood pressure. So an increase in PR causes an increase in blood pressure. So that's what ADH would look like. All right, next let's do one really in-depth one. One really in-depth one just to really drive home how involved some of these can be, because the point of this is to see all of the different ways that our body can make sure that our blood pressure stays where it needs to be. Because these hormones and these things like this are released to keep our blood pressure where it needs to get. If our blood pressure gets too low, then our body releases ADH. And what does the ADH do? We've just seen two ways that ADH causes our blood pressure to come up. And our blood pressure rises, and once our blood pressure rises back to normal, we stop releasing ADH. So these mechanisms are how our body makes sure that our blood pressure stays right where it needs to get. If it gets too low, things like aldosterone and ADH are released. If it gets too high, things like ANP are released. So there are lots of different ways that our body keeps our blood pressure right where it needs to stay. Let's look at SNS, our sympathetic nervous system. See if you can fill this one out. Actually, pause the video and see if you can fill this out before I show you what it is. And I'll tell you, it's the most in-depth one so far. All right. Hopefully you've paused the video and tried to do this on your own. Let's see. Right over here, underneath contractility, we can see SNS. So, when SNS is activated, we have an increase in contractility. I'm going to abbreviate that CONT. When we have an increase in contractility, we see contractility is one of three ways that we can affect stroke volume. So stroke volume goes up. Now when stroke volume goes up, we know the rest. Cardiac output goes up. Blood pressure goes up. But we can also see SNS is right here under heart rate. So there is a separate, unrelated way that we can have SNS have an activity on blood pressure. When SNS is activated, heart rate goes up. And when heart rate goes up, cardiac output goes up. So now cardiac output's been raised twice for two different ways. When cardiac output goes up, blood pressure goes up. But if we look a little bit harder, look over here. Sympathetic nervous system affects things like vasodiameter and peripheral resistance. So there is a third unrelated flow chart. And this is going to be sympathetic nervous system causes vasoconstriction, which results in decreased vasodiameter. When we have a decrease in vasodiameter, we have an increase peripheral resistance. And when we have increased peripheral resistance, we have increased blood pressure. When your blood pressure drops, such as when you're hemorrhaging, your sympathetic nervous system is activated. And when your sympathetic nervous system is activated, all three of these things happen simultaneously. And all three of them raise your blood pressure. All right, let me erase this. And then we'll go back and look at some more of our slides. Well, now we're going to talk about ventricular filling time. This was the other way to affect end-diastolic volume. And really, this is a big topic for lab. If you've watched the lab video, then you'll see that ventricular filling time plays a big role in stroke volume and cardiac output. When the heart is beating, when it contracts, it's pushing blood out. And when it relaxes, when it goes into diastole at the ventricles, then the ventricles are filling with blood. And then systole pushes the blood out. Diastole, we refill them with blood. Every time we go into diastole, we're refilling the ventricles. But as we beat faster, then there's going to be a shorter period of diastole. There's going to be less time to fill those ventricles with blood. So the faster the heart beats, the less filling time there is. Now, in lab, we saw there's kind of a balance. Sometimes when heart rate goes up, cardiac output goes up. But after 160 beats per minute, stroke volume wins out. As heart rate goes up, stroke volume doesn't just drop, it drops dramatically. And it actually causes cardiac output to go down the higher the heart rate over 160. And one other thing that I want to talk about is the effect on heart rate when someone is very athletic. If you are a distance runner or if you are a swimmer, I always like to see them in my class because I will often use them as kind of a case study almost. If you are or if you know a swimmer or a distance runner, then they are regularly working their heart out. And the heart is a muscle. The more you work the heart out, the stronger it's going to get. We say that it gets hypertrophy. Ventricular hypertrophy just means that the muscle of the ventricles is really big and really strong. And just like any big, strong muscle, it will squeeze harder. It will contract harder than a weaker muscle. So in endurance athletes, their heart beats so hard that their stroke volume is much higher than in someone who is not athletic. And if we're wanting to maintain cardiac output at that 5.25 liters per minute, if we're wanting to maintain cardiac output, and someone's heart is so strong that their stroke volume is very high, what happens to heart rate? Heart rate can drop. And it can drop scary low. It can get to the point that if you go to the doctor and you have your resting heart rate taken and you don't tell the doctor, hey, I swim regularly, or I run marathons, or something like that, then what you're going to do is freak the doctor out, because it's not uncommon to have heart rates in the 40s or 50s if you are an endurance athlete. As a matter of fact, one of our former tutors was a swimmer, and his resting heart rate was about 44 regularly. Now, in the average person, that is scary low to the point of dangerous. But in someone with a really strong heart, they're still maintaining cardiac output, and it is completely fine. Now let's talk about regulation of blood pressure and some other ways that our body does that. First, we're going to talk about a reflex called the arterial baroreceptor reflex, or sometimes it's just called the baroflex. Now, this kind of builds on the idea of if we have what is considered a normal blood pressure, then our body has to be able to detect what our blood pressure is at any moment. And we kind of alluded to this back when we first started talking about blood vessels, and we talked about the baroreceptors in the aortic arch and the carotid sinuses or carotid bodies. Well, the baroreceptors, baro just means stretch. Baroreceptors are stretch receptors. And these stretch receptors are constantly detecting the stretch on these blood vessels just above the heart. Remember where they were? They were in vessels just above the heart. And based on the stretch, they can determine what your blood pressure is. So the way that works is we have a normal diameter of our blood vessels just above our heart. When our blood pressure is low, then there's not any pressure on the walls of those vessels. They go kind of slack. So those baroreceptors are very unstretched. When our blood pressure is high, then we're stretching as we push blood against the walls of those blood vessels. We stretch the walls of the blood vessels, and those baroreceptors in those blood vessel walls are also stretched. So the baroreceptors detect stretch, and that stretch directly comes from blood pressure. But remember, nerve endings like baroreceptors or any other type of nerve ending, they don't know anything. All they do is sense, and then they send information to our brain. And that's exactly what's going to happen here. They're going to send information to our brain, and based on that information, our brain is going to say, hey, our blood pressure's up, or hey, our blood pressure's normal, or hey, our blood pressure's down. And then it's going to make a decision what to do based on that. But let's think way back to Bio 137. How do nerves communicate with the brain? Action potentials. And when action potentials, how did they convey, one type of information versus another? Because every action potential looks exactly like every other action potential. In a neuron, which is what nerves are, in a neuron, action potentials go from about -70 up to +30 and back. Stronger signals, weaker signals, they all go up to +30 and back. So how did we convey stronger or weaker signals? It wasn't the size of the action potential. It was the frequency of the action potential. So baroreceptors are constantly sending signals to our medulla oblongata, where those cardiac centers and vasomotor centers are. And they're constantly sending signals at a steady rate. So just kind of tap. I don't know if you can hear this, but I'm tapping on my desk. And they're constantly sending signals to the brain. And when they're stretched, they send signals faster. Or when they're slack, they send signals slower. So based on the rate or the frequency of signals coming into the medulla oblongata from these baroreceptors, then the brain, the medulla oblongata, is going to make a determination as to whether your blood pressure is up, down, or normal. Well, let's see what happens when your blood pressure is up. Well, those baroreceptors are going to have increased stretch. So that's what we're going to look at here. There's going to be increased stretch, and we're going to send faster or more frequent action potentials to the medulla oblongata. And the medulla oblongata is going to kind of interpret those increased action potentials as increased blood pressure. And when there's increased blood pressure, we need to bring that blood pressure down. So how do we do that? Well, first, we're going to activate the vasomotor centers, specifically we're going to deactivate the sympathetic nervous system. So that's going to cause vasodilation. Vasodilation, we decrease peripheral resistance, blood pressure goes down. Also, we're going to deactivate the sympathetic nervous system and activate the parasympathetic nervous system. We're going to talk about the cardiac centers. So we're going to decrease heart rate, and we're going to decrease contractility. Both of those things are going to result in decreased cardiac output. And decreased cardiac output also lowers blood pressure. So all of these three things, the drop in peripheral resistance from vasodilation, and the drop in cardiac output from decreased heart rate and decreased contractility. All three of those things are going to bring our blood pressure back down to normal. But let's see what happens when your blood pressure drops. Let's give an example that almost all of us can picture. Let's say you've been sitting on the couch for a long time, either reclining or sitting, and you're very comfortable, and you've been there for a while. But let's look at what happens when you go from reclining to standing too quickly. Well, when you're reclining or when you're sitting for a while, blood is getting back to your heart pretty easily. But when you stand up, all the blood that's down in your legs suddenly has to fight gravity to get back to your heart. When you stand up, there's a sudden decrease in venous return. And when there's a sudden decrease in venous return, then there is also a decrease in EDV, decreased stroke volume, decreased cardiac output, decreased blood pressure. So when you stand up, there's a decrease in blood pressure. And those baroreceptors detect that. And what are they going to do? They're going to send slower, fewer signals to the medulla oblongata. The medulla oblongata interprets those slower signals as, hey, there's a drop in blood pressure. I need to deactivate the parasympathetic nervous system. I need to activate the sympathetic nervous system. We get vasoconstriction to raise blood pressure. We get increased heart rate. We get increased contractility to increase cardiac output, raising blood pressure back to normal. But let's look at something more common that happens. In the elderly, this happens a lot, but almost all of us have had this happen at some point. We're sitting on the couch for too long, and then we suddenly get up to go to the bathroom, and when you stand up, what happens? You get very lightheaded. You see stars. Maybe, if it's severe enough, you might pass out. So what happened there? Well, we did detect decreased stretch because blood pressure dropped. That was sent to the medulla. Now, sometimes the medulla is slow to activate the sympathetic nervous system. This is really common in the elderly. As you age, the sympathetic nervous system is slower to respond. So there's a delay before we get these responses. And our blood pressure stays down too long. And if your blood pressure stays down too long, you're not sending oxygenated blood to your brain at the rate that it needs, and you get dizzy. So if you've ever worked around the elderly, when they've been laying in bed and they need to get up, what do? If you've ever worked in a nursing home or assisted care facility, you often hear things like sit on the edge of the bed and let your feet dangle. So when they've been laying, first they sit up and they sit there. And then from that point, they will get up a little slower. They'll often put their arms around somebody, something like that. Instead of just going from reclining to upright, they take it in steps. And that gives all of this a chance to keep up. But you don't have to be elderly for that to happen. Sometimes you can just move faster than your sympathetic nervous system can respond. Now, also we could talk about chemoreceptors, but we won't do that because that's going to be a topic for the next chapter, which is going to be respiratory. So we won't talk about those now, but chemoreceptors can affect blood pressure. Well, let's talk about regulation of blood pressure with hormones. Now, we've talked about these a little bit already. Angiotensin II, I mentioned when we were talking about peripheral resistance previously. Angiotensin II is the most potent vasoconstrictor in the body. It causes vasoconstriction, increasing peripheral resistance, which increases blood pressure. Just a few minutes ago, we talked about aldosterone. Aldosterone causes reabsorption of sodium, which causes water to also be pulled along, increasing blood volume, increasing venous return, increasing preload EDV, increasing stroke volume, cardiac output, blood pressure. ANP, we saw that it is both a vasodilator and it blocks the effects of aldosterone so we don't get sodium reabsorption. ADH, we said that it causes water reabsorption, and during things like hemorrhage, it is vasoactive. When ADH is in high levels, ADH causes vasoconstriction. The adrenal medulla. So the adrenal glands, just above each kidney, we have adrenal glands. The middle of the adrenal gland is called the medulla. The outer part is called the cortex. But the adrenal medulla is part of our sympathetic nervous system. It releases epinephrine and norepinephrine. And we've talked about what epi and norepi can do. We also have long-term renal controls. Renal just means related to the kidney. So the kidneys can have long-term effects on our blood pressure. And they will alter blood volume regardless of if hormones are present or not. So kidneys adjust blood volume independent of hormones. When your blood pressure is up, your kidneys filter more liquid out of your blood so that you pee more. When your blood pressure is down, your kidneys don't filter as much, so your blood volume stays elevated. So your kidneys are constantly filtering your blood, but they adjust that filtration based on blood pressure so that they alter your blood volume. Next, we're going to talk about the renin-angiotensin mechanism. And for this, you're going to need a full piece of paper. I recommend drawing this out. And I also recommend after we draw this out, keep the drawing handy, because towards the end of the semester, when we're talking about kidneys, we're going to take that same drawing and add to it. Because, kind of a heads up, when we get to kidneys, everyone thinks about kidneys. Kidneys make pee to clean our blood. Well, really, kidneys are going to be blood pressure part 2. So, let's draw the renin-angiotensin mechanism. We're going to look at what happens when there is a drop in blood pressure. Now, this is going to be kind of a big, elaborate drawing, so it's important the way that I'm writing these things where they are. Now, in your blood, all the time, normally not doing much of anything. Remember I said we're going to see that a lot this semester? Here's another time that we're seeing it. There's something called angiotensinogen. Angiotensinogen. Now we're going to see a few other words that look similar, but they are not the same thing. Angiotensinogen is made by the liver. Normally it doesn't do much of anything. But we're going to look at what happens when there is a drop in blood pressure detected by, of all places, the kidneys. The kidneys detect a drop in blood pressure, and the kidneys release something called renin. Renin is an enzyme. Even though it doesn't end in ACE, renin is an enzyme. Now, renin, what it does once it's released from the kidneys is renin converts. Remember that little symbol, the fish hook? Renin takes angiotensinogen and converts it to angiotensin 1 or Ang1. Angiotensin 1 or Ang1. Now, angiotensin 1 is circulating in our blood, and it is going to circulate until it gets to, of all places, the lungs. And the lungs are going to have something called angiotensin converting enzyme. And angiotensin converting enzyme takes the angiotensin 1 circulating in our blood and converts it to angiotensin 2, Ang2. Now, angiotensin II, this does two things. First, we've already seen that angiotensin II is the most potent vasoconstrictor in our body. So we get vasoconstriction, which increases peripheral resistance, which increases blood pressure. That's the fast fix for the drop in blood pressure that we have. When our blood pressure is down, all of this happens and we get a very fast response. But at the same time, there's going to be something else that happens that takes longer to occur, but it lasts a lot longer. So let's see what else happens. Angiotensin II travels to the adrenal cortex. The adrenal cortex responds to Ang2 by releasing aldosterone. Ang2 tells the adrenal cortex to release aldosterone. Now we've seen what aldosterone can do on our chart. Aldosterone tells your kidneys to increase sodium reabsorption. And if we increase sodium reabsorption, remember that caused increased water reabsorption. Because wherever sodium went, water followed it. Because sodium's a solute and solutes suck. When we increase water reabsorption, what happens? That causes an increase in blood volume. So now we should be able to fill this out from our chart. Increased blood volume, increased venous return. Increased venous return, increased end diastolic volume. Increased EDV, increased stroke volume. Increased stroke volume, increased cardiac output, and increased cardiac output, we increase blood pressure. So, what we get is a rise in blood pressure two separate ways when there was a drop in blood pressure to begin with. The first way gets there a lot quicker, but it doesn't last very long. The second way takes longer to happen, but it lasts a lot longer. Now, while we're on this picture right here, I want to talk about right up here. Sometimes we might not want someone to have elevated blood pressure. Sometimes this may be happening when we don't want it to happen. So there is a class of blood pressure medicine called an ACE inhibitor. Well, ACE is the angiotensin converting enzyme. And if we have someone with high blood pressure, we would not want this to happen. It shouldn't be happening anyway, but sometimes it starts. Now, if we have someone take an ACE inhibitor, well, ACE inhibitor inhibits ACE. And if we inhibit ACE, then we stop Ang2 from being made from Ang1. And if we don't have Ang2, then we don't get all of this top row, and we don't get this bottom row. And that's what we want if someone has high blood pressure. So, like I said, keep that picture handy. Hopefully you drew it along, and keep it handy because when we get to kidneys, we're going to take this exact picture out and we're going to add to it. So just a couple of things with disorders. Hypertension, which just means high blood pressure, hypertension comes in two forms, primary or secondary. And all that means is, in primary, the doctor can't give a definitive cause. You know you have high blood pressure, but we can't nail down the definitive cause. And about 90% of the people with hypertension have primary hypertension. The other type is secondary hypertension. And about 10% of the people have this. And this just says you have hypertension, you have high blood pressure, and we know the cause. Hypotension doesn't get as much attention. Hypotension is low blood pressure. Now, earlier, let's go back to our slide back here with the elderly. This is a type of hypotension when you stand up too quickly and you get that dizzy feeling. Sometimes that happens all the time. And that's called orthostatic hypotension. Orthostatic hypotension. Sometimes it's also called postural hypotension. But hypotension just means low blood pressure. And this can be a problem too, because if you don't have adequate blood pressure, well, now you're not able to provide nutrients to your tissues. You're not able to adequately oxygenate your tissues. You're just not able to supply different parts of your body. You also might not have the pressure needed to have your blood filtered at your kidneys. Hypotension is just as big of a problem as hypertension, if not more so. Next, we're going to talk about circulatory shock. And circulatory shock, there's different types of circulatory shock, but what they have in common is your blood cannot circulate normally. One type is hypovolemic shock. In hypovolemic shock, you don't have adequate blood volume. Maybe it's a hemorrhage. Hypovolemic just means low volume. So it's a drop in blood volume. And if you don't have adequate blood volume, then that blood can't be circulated normally. Next is vascular shock. In vascular shock, you have normal blood volume, but you have extreme vasodilation. So your peripheral resistance drops a lot. And that will, in turn, really lower your blood pressure, and your blood can't be circulated normally. Finally, cardiogenic shock. Here, again, you have normal blood volume, but your heart is not adequately pumping to circulate your blood. So your heart is the problem in this case. All right, so that is the end of Unit 1. Everything up to this point is fair game for the exam. Everything after this point will not be on Exam 1. All right, hopefully everything makes sense. If you have any questions, let me know.